Okay, so this unit is extending upon what we learned about in third quarter on energy and waves. So now we're going to extend what we learned about energy and waves and really look at how light energy is can create different images and how light energy can create the different colors that we see. Okay, so we are working with target 36, apply how waves behave when they interact with mirror and lenses. So we're now going to look at how light waves refract off mirrors and lenses. Okay, we did a little bit of how light waves refract off mirrors, so that will be a bit of a review, but the lenses is new. Okay, so our essential question for the day is how do mirrors and lenses create an image? So let's review what we learned about third quarter with waves and energy. Okay, so when we looked at light waves as they hit a plane mirror, remember we did the lab where the law of reflection states the angle of incidence equals the angle of reflection. So if you have incoming rays that hit a mirror, they are going to reflect back at equal angles, and that's what this picture is showing you. Here's our light that is having the incoming rays, they're reflecting out at equal and opposite angles. Okay, now in a plane mirror, remember you still see an upright image, but it's reversed. That's why whenever you look at the mirror, you are looking at a reversed image of yourself. And this just goes to show you why. If we've got light coming in and it reflects back, remember you extend the reflecting ray across the mirror. Okay, so this part of the B is now over here, and the bottom part of the B is here. So that's why it's a reversed image. So that's a review of the law of reflection. That's going to be pretty important when we start looking at lenses. Okay, so remember a plane mirror is a flat reflecting surface. The image you see in the mirror seems to be behind the mirror. That's because your brain processes the light rays that enter the eye. They always assume the light rays travel in a straight line without changing direction. So the image is upright and it's reversed, just what I showed you. Now, if we take a look, this is going to be a review from a little bit of new information and review. I'm going to have this link underneath the video so that you can go through it and read it on your own. But that's what I would also like you to do, because I'm not going to go over this website, but you do need to review the law of reflection. So again, this website will be linked underneath the video. Okay, what I really want you to do is start looking at how the image of an object works on a plane mirror. Specifically, when you get down to the bottom here, it's going to give you some practice on what image will see what reflecting off a mirror. So if you take a look at this bottom example, you've got light reflecting rays that are bouncing off the mirror. And remember, the only people who can see the image are those where the reflecting rays hit the eye. So what I want you to do is go to this website, read through it, and then you're going to do just a quick review just to make sure that you understand who will be able to see what based on the law of reflection. So please make sure you do that as practice, okay, because that's going to help you understand how lenses work. So again, this website will be underneath the video. You'll need to go look at this, review it, and do some of the practice for a review. Okay. So now we're going to start talking about some terms that we'll need to use when we talk about lenses. So the focal point, remember the optical axis is also called the normal, and you drew this in your lab with the law of reflection with the mirror. You put a piece of white paper and you measured the center of the mirror and then you drew a line perpendicular to the mirror. That's called the optical axis. The focal point is the point on the optical axis where rays traveling parallel to the axis pass through. So it's where the rays intersect. And this is going to be pretty important when we start looking at our lenses. Okay, so if you look here, The focal point is on the optical axis where all the rays, the reflecting rays, are intersecting. And we'll do a lot of practice with this, and you'll see how you can find the focal point. Now, the focal length is the distance along the optical axis from the center of the mirror or lens to the focal point. So wherever the lens is, which is right here, it's kind of hard to see it because it's really lightly shaded. Okay, here's where the lens is. Okay, the focal point is right here. So the distance from the focal point to the lens is called your focal length. So now let's take a look at mirrors. Mirrors are going to refract or bend light. Remember, a plain mirror just reflects light, but a lens is going to bend it, and it's going to cause those bending of reflecting rays to change what you see. So we're going to look at different mirrors that are bent, and then we're going to look at lenses that are bent. So a concave mirror is curved inward, just like this picture shows. It causes the light rays to come together or converge. Okay, so we're going to go through the different types of images that you will see with a concave mirror. Okay, so concave mirrors usually invert or put the image upside down. So examples of concave mirrors, like a spoon, is going to invert your image, make you look upside down. There's all different types of mirrors that will do that, as well as some of the ones you see in like convenience stores and stuff like that. Most of those are convex, but we'll get there in a second. But these are all examples of concave mirrors. Okay, so let's think about how concave mirrors work. Okay, so concave mirrors depend on where the image is located away from the lens. So remember, let's take a look at this picture right here. The focal point is where images or reflecting rays converge. Okay, so the focal point can be found on a concave mirror. You will do this in a lab. You will actually find the focal point. That is where you will no longer see an image, and you'll see why in a minute. So the focal point can be found whenever you put an image on the optical axis. Remember, the straight line in the center of a mirror, perpendicular to the mirror. And wherever you can't see the image, that's the focal point. So right here, they found the focal point to be at this distance. So the focal length would be the distance from the focal point to the lens. Now C is called the curvature. C is greater than 2 focal lengths, and you'll see why that's important in just a minute. So if we have an object that's an arrow, okay, whenever you draw these, you will draw 2 incoming rays. The first ray you will draw is the one that is parallel to the optical axis. So you draw that in parallel. If you draw it in parallel, it will hit the mirror, it will bend or refract, and the refracting or reflecting ray will always, I'm sorry, these are reflecting, not refracting, because mirrors always reflect. It's the lenses that refract. I'm sorry. So the reflecting ray coming off a parallel incoming ray will always travel through the focal point. So when you draw the parallel incoming ray and it hits the mirror, it will reflect back out through the focal point, and that's what they've drawn here. The other incoming ray that you're going to draw is the one that goes through the focal point. If it goes through the focal point and hits the concave mirror, it will go back out parallel to the optical axis. So see how these are opposites? Incoming ray parallel, reflecting ray through the focal point. Incoming ray through the focal point will reflect out parallel to the optical axis. Those are the only 2 rays that you will need to draw, those 2 incoming rays and reflecting rays, to find the size and what the object looks like. Okay, so let's show you how there's different ways that these objects are going to look depending on their distance away from the focal point. So the first one you're going to look at is if an object is greater than twice the length of the focal point. Okay, so twice the length. So if you notice, the object right now is 2 times the focal length past the lens. You will always get an inverted or upside down image, and it will be smaller than the actual object. So let's take a look and see how that works. Okay. And that C stands for center of curvature, so that's past 2 focal lengths. All right, so this picture is going to show you incoming ray parallel goes through the focal point. When it does that, remember that's the tip of the light, that's why it's inverted. And then the image that's always formed, you always draw it going from where the reflecting rays intersect, right here, to the optical axis. So just like it's doing here, because this reflecting ray is the tip of the candle, that's why you draw the tip of the candle right here, because that's the reflecting ray. And then you draw the image going to the optical axis. And if you look, it's an upside down image and it's smaller. So a concave mirror works if it's 2 focal lengths past the lens, then you will get an inverted, smaller image. So that's why you can take a spoon and move it farther away from you, and you will start looking smaller and smaller upside down. Okay, so now let's look at if an object is in between twice the focal length, but it's still in between the focal point. So let's take a look at that. You're going to get it inverted and bigger. So I'm going to show you why that works. So if you look at this object here, here's twice the focal length. That's called the center of curvature. Okay, so remember our previous image was located over here. This is in between the center of curvature, twice the focal length, and the focal point. Okay, so same thing. You're going to draw the incoming rays parallel, then reflecting ray through the focal point, incoming ray through the focal point, reflecting ray parallel. Where those 2 reflecting rays intersect, right where my arrow is, that's where the image is drawn. Now if you notice, the reflecting ray top of the candle is down at the bottom, so that's why it's inverted. And then you draw the image going from where the reflecting rays intersect to the optical axis. And if you notice, you've got a larger image. So when an object is in between the center of curvature and the focal point, you're going to see a larger but inverted object. Okay, so now we're going to put the object right at twice the focal length, or it's called the center of curvature. You will see an inverted but same size object. So let's see how that works. Okay, again, we're drawing parallel incoming rays, reflecting rays through the focal point, and then incoming ray through the focal point, reflecting ray parallel. Okay, where those 2 reflecting rays intersect is where you draw your image. So the top of the candle is down below here, so that's why it's inverted. You draw it up to the optical axis, and you'll notice you've got a same size object. So using a concave mirror, you can have a same size image, but it will be inverted at the center of curvature. Okay, so now we're going to put the object right at the focal point. So you remember earlier I said you can find the focal point because that's where no image is going to be seen in that mirror. And so you can find the focal point where you won't see an image, and then you can find your focal length, and then you can find your center of curvature. Okay, so let's take a look at how that works. You're not going to see an image when the object is right at the focal point. And here's the reason why. If I put the image right at the focal point, notice, oh, it keeps moving on me, the parallel incoming ray will reflect back at the focal point. You can't draw an image because the image is right at the focal point, so you're not going to see a reflecting image. Okay, so when the object is at the focal point, no image can be seen because the reflecting rays will not intersect. They'll intersect right on the optical axis, so you can't see it. Okay. Now there is one way that using a concave mirror you can actually get an upright and bigger image. The only way to do that is when the object is in front of the focal point. Okay, so let me see if I have a picture down here. Nope. Oh, this one right here is showing you no image at the focal point. See how all the reflecting rays are right there? You can't see the image. Okay, so let's look at when it's in front. Okay, so notice right here, here's your object. It's in front of the focal point. So you do the same thing. Okay, you draw a reflecting or an incoming ray parallel and then back through the focal point. The reflecting ray is through the focal point. Then you draw the incoming ray at the focal point out parallel. Now if you notice on the left side of the mirror, the reflecting rays will never intersect. So just like we did in our experiments in third quarter, if you extend those reflecting rays past the mirror, you will get an image. And if you notice, this reflecting ray, okay, is at the top. So that's where the top of the candle is. Okay, so you've got the top of the candle. You do the same thing where those incoming reflecting rays intersect on the other side of the mirror. You draw, that's where the image starts, and then you draw it as big down to the optical axis. So if you notice, you've got a upright but larger image. So that's why if you move a spoon closer to your face, you can see an upright and larger image. So those are all the different images that form from a concave mirror with reflecting rays. Okay, there's a lot of them, but you're going to get a lot of practice with them. And once you learn how to draw the incoming rays and reflecting rays, it's very easy to figure out what type of images form based on your distance according to the focal point center of curvature. Okay, so now let's look at a convex mirror. A convex mirror, you will always see an upright image, but it's always going to be smaller. So let me show you examples of convex mirrors. So the mirrors in your cars, those are going to be convex mirrors. Okay, mirrors that you see in stores, those are also going to be convex. Okay, so now let's see how those work. Okay, so let's take a look at this picture. Now, if you notice, the focal point is on the opposite side of the mirror, and the reason why, if you look at the mirror from this side, that's a concave mirror. The focal point is always located on the inside of the mirror where it curves in. Okay, and again, you can find that by where there's no image. So if the object is over here and you've got a convex mirror that curves outward, you're going to do the same thing. You're going to draw an incoming ray parallel. The reflecting ray will go through the focal point. Then you're going to draw the next incoming ray through the focal point and out parallel. And where those two intersect is where you have your image. And if you notice, it's an upright and smaller image. Okay, so convex mirrors will always have an upright, smaller image. Okay, now we're going to take a look at lenses. So remember, mirrors will reflect light. Lenses are going to bend the light, and so they're going to refract. So let's take a look at some lenses. Wrong one. Oops, wrong one. Okay. So this is a lens, and there's two types. There's your convex and your concave. So obviously the convex curves out, the concave curves in. Okay, just similar to your mirrors. Now, on a plane lens, you're going to see just the same type as you would a plane mirror. But if you look as I start to move, a convex lens starts to bend those reflecting rays at a certain point. Okay, just like that. And then if you look, plane mirror, then we go to concave. Concave bends the reflecting rays outward. So let's take a look at our eyes. We have what's called a convex lens in our eyes because it curves outward. Remember, a concave lens will curve inward. So this is a normal-sided if your eyes work correctly. You see the letter R, you see a same size but inverted image. That's what a convex lens will do. Now let's say that some of you have to wear glasses or contact. It's usually because there's something wrong with your convex lens. If you're long-sighted or far-sighted, if you notice, normal-sighted, those reflecting rays intersect right where the R is supposed to be seen. And then what happens, we don't see things upside down. You guys all know this. I forgot to tell you this. But there's an optical nerve that sends this message to your brain. It automatically reverses everything you see. So your eye sees everything upside down, but the message that gets transmitted from your optical nerve to your brain reverses that image so that it's upright. It's pretty cool that our body works that way. So let's get back to if you're farsighted. Notice those reflecting rays don't intersect where the image is supposed to be. That's why it's hard for you to see. Okay, so you have to fix it. So if we add a lens, if you go to the doctor and they find out that you're long-sighted, they have to fix it. So what do you think they fix it with? A convex or concave? Well, convex will start to narrow down those reflecting rays. If you notice, there we go. So your eyesight is fixed with a convex lens. So that's what your contacts or glasses will do. Now let's look at short-sightedness. That means that this is where the image you see, but it's supposed to be there. Okay, so you have to fix that with a concave lens to get those reflecting rays to widen up so that you can see the image. I went too far. Okay, so that's what happens when you have something wrong with your convex lens. It has to be corrected with either a convex lens or a concave, depending on whether you're long-sighted or short-sighted. Okay, so let's take a look at the two different types of convex lenses and concave lenses. The convex lens creates the same images as a concave mirror. That's one easy way to remember. Convex lens, concave mirror. Concave lens, convex mirror. So remember, the concave mirror had all the different images depending on where the object was located. So let's take a look at that and see how that works with your lenses. So if you have an object that is past 2F, past the center of curvature, remember you will see an inverted image and it will be smaller. So here's how this works with the lens. You draw an incoming ray parallel to the lens, then it's going to reflect through the focal point. Notice the focal point on lenses are on the opposite side. And remember, you can find the focal point where you don't see an image. So where you don't see an image, that distance from here to here is the same as over here. Then if you draw an incoming ray through the focal point, okay, through the focal point, it's going to hit the lens and reflect out parallel. Now notice, the lens, you have to draw a line down the center of the lens because that's where the light ray refracts. It doesn't refract here. It refracts at the center of the lens. So when you draw that incoming ray parallel, you got to go to the center of the lens, then reflect it out through the focal point. Same thing here. Draw the incoming ray through the focal point all the way to the center of the mirror, reflect out parallel. Where those rays intersect is where the image is. And notice, if this is the top of the arrow, then that means this is bottom part is the top. That's why it's inverted. And you'll see an inverted, and it will be a smaller object. So now let's move our object in between center of curvature and the focal point. Okay, draw an incoming ray parallel, reflecting ray through the focal point. Okay, incoming ray through the focal point, outcoming ray parallel, and for some reason this doesn't want to show the image. There we go. Okay, I moved it back. There goes out, reflecting ray parallel. You've still got an inverted, but now it's a larger image. So the closer you get to the lens, you're starting to get a larger image until you get to the focal point and the reflecting rays will never intersect. So that's why you see no image. Then if we go in front of the focal point, see if I can get an image, there we go. Okay, draw an incoming ray parallel. It's going to reflect out through the focal point. You extend that over, they should have extended over to this side. Then you draw an incoming ray through the focal point. It comes out parallel. These two will intersect. They should have drawn the reflecting rays. Over here, you're going to see an upright but larger image. So a convex lens makes the same images as a concave mirror. So here are some pictures that show you just what I went over with you. If you want to pause the video and draw these images, you're more than welcome to. I will also attach some of the links so that you can see them off the website as a review. Okay, so now let's go to a concave lens. Well, if a convex lens is just like a concave mirror, then a concave lens creates the same image as a convex mirror. You will see an upright, smaller image. Okay, so that's what this is showing you right here, a concave lens. If you draw the incoming ray parallel, it's going to reflect at the focal point. Okay, draw an incoming ray through the focal point, out parallel, you're going to see an upright but smaller image. I think one of these shows that. Yes, upright, smaller, where they intersect. It's kind of blurry right there, right here, and right here. Okay, the last thing I want to talk about is how we describe the images that are formed from lenses and mirrors. A real image is where light rays converge. That's where the reflecting rays intersect on the other side of the lens. And they will always create an upside down image like your eye does. That's called a real image. And remember, your optical nerve will reverse that. So if you have an inverted image, this is usually a real image. Okay? Doesn't matter about same size or bigger or smaller. But if it's inverted, it's a real image. A virtual image is locations from where light appears seem to have converged as well, but they converge on the same side as the object. And it will always be an upright image. So if you have an upright image, that's a virtual image. If you have an inverted image, that's called a real image. Okay, so hopefully after the presentation, you'll have a better idea on how light waves interact with mirrors and lenses. Remember, mirrors, they reflect. Lenses, they refract. And depending on whether it's a concave or convex, that's going to determine what type of image you're going to see. And you're going to get a lot of practice with this. You're going to have a lot of practice drawing the incoming rays and the reflecting rays and drawing where those rays intersect and drawing the image. I will attach the websites that I use to show you the animations underneath the videos so that you can go back and see how to draw those incoming and reflecting rays. So you can use those resources underneath the video to help you on your practice. So that is Learning Target 36. Apply how light waves behave when they interact with mirrors and lenses.